Welcome back. This is a part D of concept video for section 16.6. Find the surface, we are going to do example number 10 in this video. Find the surface area of a sphere of radius A. So you have done surface area in several ways in earlier calculus classes. You have seen this idea in chapter 8. Where we define arc length and surface area by rotating a curve about the x-axis or y-axis. And you have seen this same idea also in parametric representation in chapter 10. Now we are going to do this in using the parametric representation of the sphere, which we have seen before. So in the same section, we derived parametric representation of a sphere. That is what we are going to be using to find out the surface area. So parametric equation of the sphere, when we derived in this section, you might remember that we said this line here, it's a parametric representation of the sphere using phi and theta, which are used in spherical coordinates. So the restriction on phi are 0 to pi and restriction on theta is 0 to 2 pi. This one is what we are going to be using in this particular problem, along with the formula that we derived. Surface area of a surface, we said that it's equal to A of S, which is double integral over D, magnitude of the vector Ru cross Rv dA, if it is parametric representation. That is what we are going to be using in this example 10. So we will start with the parametric representation of the sphere. So the parametric equations of the sphere is x equal to, the radius is given to be a, so it's x equal to a sine phi cosine theta, y equal to a sine phi sine theta, z equal to a cosine phi. Now, what is the parametric domain? Parametric domain is a nice rectangle because it is made up of phi comma theta, where both phi and theta have definite limits. So it becomes a parametric rectangle. Now, for the formula, what formula are we going to be using? Area of the surface or area of the sphere in this particular case, surface area of the sphere, of the sphere, in this case, the formula that we are going to use is double integral over d absolute or length r phi cross r theta d phi d theta. This is the formula we are going to be using. You know the limits for phi and theta from this step. So let's compute r phi cross r theta. So r phi cross r theta is equal to determinant I, j, k, then you have x with respect to phi y with respect to phi, z with respect to phi, or partial derivative with respect to phi. Then same thing, the second row will be the components of our theta, all partial derivatives with respect to theta. To show one example, so this is going to be a big expression here. So when you do, if you want to find out, let's say, dou x by dou phi. So I'll show you one example. You can complete the rest of them. So this is how you do. X is given to be a sine phi cosine theta, a sine phi cosine theta. We are differentiating this partially with respect to phi. So you are differentiating this with respect to phi. So a cosine theta is constant. They're going to differentiate sine phi with respect to phi, which will be cosine phi. Then when you do y, which is equal to a sine phi sine theta, when you do dou y by dou phi, so it is going to be a sine theta, which is constant, a derivative of sine phi, which is equal to cosine phi. Then z is a cosine phi. When you do dou z by dou phi, that would be negative a sine phi. So like this, you also want to do with respect to theta, then you can substitute them in these values. So I'm going to just substitute these values here. I, j, k. Then the second row is what we have found out here. A cosine phi, which is this value that we got here. A cosine phi, cosine theta. Next, a cosine phi, sine theta. Next, it's negative a sine phi. Same way, if you do the same process for with respect to theta, and you're going to get negative a sine phi sine theta, then a sine phi cosine theta, then 0. If I expand this in terms of I, j, and k, I will get, please check this, it's a square sine square phi cosine theta I, then plus a square sine square phi sine theta j plus a square sine phi cosine phi k. All we have done is r phi cross r theta. For the formula that we use, we need the length of this vector. So when you do length of this vector, so which means it's square root of x component square, y component square, and so on. So it's a to the power 4 sine to the power 4 phi cosine square theta plus a to the power 4 sine to the power 4 phi sine square theta plus a to the power 4 sine square theta sine square phi cosine square phi. So if I look at the first two terms here, a to the power 4 sine to the power 4 phi is common. If I remove that, a to the power 4 sine to the power 4 phi, then if I combine the first two terms, I get cosine squared theta plus sine squared theta, which by Pythagorean identity is 1. So, using all of it, you get square root of a to the power 4 sine to the power 4 phi by combining the first two terms. Then you are left with the third term, a to the power 4 sine square phi cosine square phi. So in these two, you notice that a to the power 4, of course, is common. And also sine square phi is common. So if I do that simplification over here, a to the power 4 sine square phi one can pull out. So I'm left with sine square phi plus cosine square phi from the second term, which is 1 by Pythagorean identity. So when I take the square root, it is a square um, absolute sine phi technically, but phi lies between 0 and pi, so between the first quadrant and the second quadrant only. So it is going to be positive. So I can remove the absolute sign and write that as just sine phi. The reason being phi lies between 0 and pi because of that. So area of the surface, in this case area of the sphere, uh, is double integral over d absolute r phi cross r theta dA. So we know the limits for the domain. So theta from 0 to 2 pi and phi from 0 to pi. We evaluated the inside, which is a square sine phi d phi d theta. So it is separable variable, separable. So I can take the a square out, and then 0 to 2 pi d theta can be taken out as well. Then 0 to pi sine phi d phi. So this will be a square times 2 pi. Then integral of sine phi, that is negative cosine phi between 0 and pi. That's a square times 2 pi times negative cosine of pi minus of minus cosine 0. So it is 2 pi a square times cosine pi is negative 1, negative of negative 1, positive 1, positive 1. So it becomes 2 times 2 pi a square. So 4 pi a square is 4 pi radius square, which is what we know about this surface area of a sphere. So what we have done in this problem is the parametric way. So representing the sphere in the parametric form, then finding the area of the surface using the formula of parametric representation. Hope this video helps. See you all for the next section 16.7.